I'm now recording in OBS. But one thing I'll say is that GNNs are like super slow, so I'm not sure if it'll be the best. Cause yeah, nowadays like people use like transformers in GNNs, so it might not be like the optimal strat. Yeah. Okay, so back to skipgram. So basically we have like a one layer neural network to predict all the other nodes in the graph along a path. But yeah, kind of like, I think you might notice some limitations of this. Like, for example, it expects that a one layer neural network has like enough representation power to represent a graph. And also, we need to like worry about hyperparameters, like how many random walks should we do, and how long for, like what the window size should be for here, like how many nodes should we predict along each path, kind of like that. So like overall, like it's a nice approach, but it's like a very sklearn, like scikit-learn, like a very basic approach. So to combat this, we kind of introduce GNNs, and this is like the first type of GNNs mentioned in the paper. So I like to clarify, this isn't like all GNNs are, but this is like one of the main parts of GNNs. And for this, I like to introduce this paper not mentioned in the original paper called House Gang. And I like to talk about this paper just because I love the visualizations in the paper. So I think it'll help, at least it helped me when I was understanding GNNs before. Okay, so the task is, yeah, let me see if I have questions. Yeah, I guess it's like a potential approach. Oh, interesting. Yeah, I might look at this later. But yeah, so basically for the task for house game, it's like you have a network or like a graph of like rooms. So let's say you want to have a kitchen and have it connected to a living room. And let's say we want that living room to be connected to a toilet or something like that. We can encode these as like where the nodes are like the rooms, and like these edges are like saying this room is connected to this other room, and we say like all these are like, this is like a room layout that we want. And from this, we want to generate like buried room layouts that fit this. And I think like if you are like worked with like, let's say stable diffusion or GANs before, you might be wondering like how exactly is this like possible? Like it's like so much constraints that the network has to like go through in order to do it. And like if you try this with like stable diffusion, I think it won't be able to get all the complexities of like which rooms are next to which like accurately. So at least I found this to be an interesting problem. And the way the paper solved it was for every single one of these nodes. So let's say this is a living room. It generates one room. Like, so like this room generates one room here. And then finally, when we wanted to make the final room layout, we just add them all together. So this room maps to here, for example. And this room maps to here. But kind of like, I think like one question you might be having is how exactly does like this node, like this room, know that it's not overlapping with like, say, rooms like over here, or like if it's like actually connected to these two rooms. So here's where the crucial concept of message passing comes up in like GNNs. And so the basic idea is we start out with like random noise with some information as the input to all these nodes. So all of these nodes start with random noise and some information. And then we update each of these representations through the current representation at this node. and the sum of all the neighbor representations. So it's concatenated. This is the sum of all the neighbor information. And finally, the sum of all the nodes that are not the neighbors. So basically, like every iteration, it gets information from all the nodes around the graph. And then after like in this case, 4 iterations, it knows like, oh, the room I generated here won't be like on top of any other room. It'll be connected to the proper parts, and it won't be connected to any of the parts that I don't want to be connected with. Basically, it gets all that information through this thing called the message passing network. Yeah. So basically, kind of like this kind of updating like aggregation stuff is specific to this example, but in general, like at least for the initial GNNs, it follows 2 steps. First of all, we aggregate the information. So that'll be this part. So we aggregate the current neighbors and non-neighbor information. And next we update the representation given this aggregation. So that'll be, we pass it through a CNN to get this. Now for like the aggregation, we can be like a bit more creative. Like for example, like there was one paper mentioned called the graph attention networks, where instead of like just doing like simple aggregation like this, we have like an attention model predict like the contribution of each part, like how much we should attend to this one and stuff. But yeah, overall, like this method is cool and it's great, but it has limitations. And the paper called these networks like neighborhood aggregation based models. And the limitation is that if the graph is too large, like it can only find like local neighborhoods. But like, so like if like it has like 1,000 nodes or something, every node won't know like every other node in a way, because it can't, information just can't flow that fast, you know. So like maybe with like a lot of iterations, it can do it. But for like a very large graph, we need another solution. But one thing I want to highlight is that there is a bit of a benefit here in that in this message passing network, you only see like 3 entries, at least in this case. But like even if we get all the neighbors and stuff, the computation is just like O(n), where when n is like the number of nodes. So basically it's like very efficient. Like for example, if you were to do like GPT-4 or something, it's an attention network, so it will need O(n) squared, because we have to like calculate all the relationships between all the nodes with all the other nodes, basically. So yeah, this is like one important benefit that doesn't appear in the other models we talk about. Okay, so next, kind of like the main work that I don't think this is the first paper that explored this, but one of the main papers that kind of like brought graph transformers about is, do transformers really perform bad for graph representation, by Microsoft. And yeah, this is around the time when like the transformers and stuff were like exploding in popularity and in leaderboards for images and text. But like, for some reason, on the top leaderboards for graphs, there were still those neighborhood aggregation based methods. So yeah, the people at Microsoft kind of thought of the question, like, how can we modify these pure transformer stuff so that it can work with graphs? Yeah, is there any questions? Graph representation learning. Sorry, for it isn't necessary to initialize randomly, but in this case, it's a GAN. So basically, there is like a discrimination stuff, but basically here, in this case, it's a GAN, so we usually initialize randomly and then generate images. In the works we're gonna talk about in a bit, basically you can initialize based on like text encoder embeddings of like, yeah, basically text encoder outputs, so that the GNN has some idea what kind of like what the text is talking about and stuff. But this is just a special case. Yeah. And does the model train for specific graphs somehow used for arbitrary initial graphs? Kind of like one thing that I found interesting in this paper was that it found that graph neural networks are not like that good with out of distribution stuff. So I think like you can't if I understand your question right, I don't think you can like do something like ImageNet classifiers for graphs where like you can have like a pre-trained graph and like apply it to like an arbitrary graph task maybe. Yeah. Oh yeah, good point. Yeah, it's ON plus M for edge. Yeah, yeah. Yeah. I want to talk about graph attention now. So yeah, now a bit of a background on like attention. So basically how attention works is given like input like tokens and stuff, we get a query vector, a key vector, and a value vector. And basically this whole stuff here makes something called the attention matrix. At least I think that's the name, where it finds like how much attention each token should pay to each other token for like the next step. And so it's basically like each row sums to 1 in a way. So it says 0.9 on this token, 0.05 on this token, and so on. And then we multiply by this value matrix to kind of like get like a arbitrary kind of like, yeah, like a updated representation where all the attentions are paying attention to the proper parts. But yeah, I did mention in the previous slide that this transformer stuff exploded in text and images, but for images too, it wasn't able to work with transformers from the start. Correct me if I'm wrong, but kind of like from what I found, the first like vision model that actually worked with transformers that outperformed GNNs and stuff was this swing transformer. And basically the idea was, let's kind of shift the windows a bit to kind of like propagate like information like through the attention layers. I won't go to like into too much detail with this, but the main idea I wanted to like take home is that basically like a vanilla transformers don't have like any bias in them. But like when we kind of apply to like a new modality like vision and graphs, we have to give something called an inductive bias to kind of like make it perform well in that modality, although it's kind of like a bit biased in a way. Yeah, but overall like a inductive bias is like very helpful for like making it like work in a certain domain. Yeah. Yeah. So for graphs, yeah, there's a lot of equations on this slide, but let me go through it. So first about is centrality encoding. So basically this is added to the node features before we go through the Q, K, and B. But basically the idea for this is, let's say you are on like a social network for Twitter or something, right? And then you have somebody with 0 followers, and you have somebody like Taylor Swift who like, I don't know, controls the, like has, I don't know, billion followers or something. But basically the idea for this is, I think Taylor Swift is way more important for like predicting stuff than like people with 0 followers. So basically this encoding is, you have like the original node, and you have like how many people are like following you. So like an embedding of that number, and how many people you are following. So like an embedding of that number too. And then you just add it. For like undirected graphs where like there's no direction, you can just have like one z here, or like one embedding vector here for degree. Now for like the positional, second of all, for positional encoding, basically this is here, this is something for attention networks that is kind of required so that the neural network knows like word order basically. So for example, for like text, basically we want to know the distance between each token. So for text, we just do like 1, 2, 3, 4, 5, 6, 7, like in that row. But for graphs, the question is like, how do we find the distance between each node in a graph? And the interesting thing the authors did was, why don't we just get the shortest distance between each node, like this, and then we just encode that distance as the distance between each node, which honestly like is very simple, but I just thought it was pretty interesting. So like B1 and B4 is separated by a distance of 2, because that's the shortest distance. So yeah, that is encoded here. For the edges, it gets a bit more complicated in that, and I don't think I fully get it. But basically, there's like this initial learned vectors for the node features. And then along the shortest path, it kind of does a dot product with like the edge learned embeddings. They kind of like, I think it kind of, the idea is that it gets like how important the network thinks that path is, or something like that. But overall, these get added after the attention matrix is computed, because basically you can't add it here because the size of it is n by n, basically like this. Any questions? Yeah. honestly, mostly anything can be solved with this, I think. Honestly, that's a great question. Kind of like, I approached, in the paper it was a bit approached like you can't like find like a good order for graphs. So like for some papers they just do something like text, where you have like an arbitrary order of nodes, and you apply like a positional embedding to them, like 1, 2, 3, 4, 5, 6. But yeah, and also that, yeah, like if it's like a weighted like graph, you might be able to do something a bit like that. Oh no, it's like distance between graph nodes. Yeah. Yeah. So yeah, so that kind of like did good. It got like SOTA and stuff, but the kind of main limitations are like, unlike the previous one, there's like a bit of information lost when kind of like you do this, because you kind of like lose a bit of information, or like lose a bit of focus on like what the neighboring nodes are compared to say the neighborhood aggregation one. And yeah, I didn't mention here, but I will mention later on, but the obvious limitation is like it's now O(n) squared, because you have to calculate like a big attention matrix. So kind of like one idea that people had was, maybe we can get like good representations with self-supervised learning. So basically what self-supervised learning is it's a bit like if you heard of like Dino, or for image models, or like Clip, basically those are like self-supervised learning, or in particular something called contrastive learning. And in this paper, it explores like, basically how it's done is like you have like an image, and you kind of rotate it a tiny bit, and then you pass it through the network, and you want like the representations to be the same. So in this case of a graph, we remove some edges, and then we pass it through the network, and then we expect the representations to be the same. Basically, it's something like that. But yeah, kind of like there are some limitations, and the main one that the authors tried to drive home is that these networks that I mentioned previously, all of them do not generalize to out of distribution data. So you can't like apply it to like a new modality or anything. Or even you can't even in this case, like if the graph size is significantly different, it won't it won't work because it's like a significantly different set of data in a way. And also, yeah, can't scale past the size the graph learned. And also, yeah, O(n)(squared). Kind of like one solution to this that might be interesting was there was something called Graph Mamba. And basically, Mamba was like a pretty famous paper where instead of like doing like transformers, you do like an approximation, which I think lowers the complexity to O(n) from O(n)(squared), but with like similar results. And there is a paper for Mamba in graphs, which might be like a pretty interesting direction. I don't know if it's like a promising direction or not, because I haven't like fully gone through it. But yeah, just to mention. But yeah, kind of like finally we got to here. But the idea that the authors had was, can we like just plug in like a large language model to graphs to make them work with like out of distribution data? Oh, is there a question? Yeah, that's like a great question. Honestly, I'm not sure. I think like the neighborhood aggregation based methods are typically used because those are not O(n)(squared, so it might be simpler. But yeah, maybe partitioning still. Oh, so basically the idea is like, so the question is, why is like geometric distance in the graph like shortest distance preferred over like similarity in like vectors? And like the idea is you don't assume you have the vectors in the first place. So yeah, you just don't assume you have the learned embeddings of the vectors in the first place. You just have the graph, and then you want to learn the embeddings. Like you want the network to learn the proper embeddings. So yeah, if you have the embeddings, it might be a good solution. But also like you want the integer, because basically it's like an embedding. Basically an embedding that you put in an integer and you get back a vector, like a learned vector. So yeah, basically you want the integer distance metric, and the shortest distance is pretty good. And where do we get the graph from? Oh, so basically the idea is like, how can we use LLMs to improve graph modeling? And like, I guess your question is like, what kind of graph tasks are there? But there's like recommendation systems or like robot task planning. Like those are like how tasks are. But I think I'll explain those like later on in the dedicated sections. Yeah. Okay, so to combat this kind of like out of distribution data, I kind of like the idea is to plug a large language model like inside like a graph neural network. So yeah, that's the first one. The first of the three categories of like doing graph machine learning with like LLMs is having the LLM be like an encoder. So yeah, kind of like the first like naive approach to do this is, given like a text, you have like a, let's say, an open source LLM, and you get like the text features, and then you use these text features So this is like a graph nodes where like every node has text, and you use it to initialize the GNN, and then you process the GNN to get the good representations. So basically, it's a bit like this, but every node is not initialized with noise; it's initialized with text features. And yeah, and kind of like there are slight improvements to this in this paper where they enhance the text with like ChatGPT and stuff, but overall like it's like the same idea. And another kind of like another a bit more interesting way to make like LLMs kind of like work with graphs as an encoder is like given like the text features, we did the same like embedding stuff for the text features, but a slight like a slight new thing in this paper is we have the LLM modify the graph so that kind of like we can have like more the GNN has like an easy time processing the graph, and then we finally plug it into a GNN. So yeah, that's another strategy. And kind of like one kind of like more interesting strategy was like a one paper that was referenced a lot called One for All. And the basic idea was given like a network and like the descriptions and stuff, you have a LLM add a new node with like questions like, is this paper about bio? Is this paper about CSAI? And like all these kind of like like a query kind of like node embedding thing, if I understand correctly. And then using this, you can have the single GNN do multiple tasks given like just these inputs. So basically it kind of like it does exactly what we asked for. It does like it does kind of like generalize the out of distribution data with just LLMs. But yeah, any questions so far? Okay. Okay, so the limitations of these papers are pretty simple. Basically, it requires us to train this GNN, which means that we have to have labeled data for the graph neural network to train on. So the next approach that was popular was, can we just have the large language model predict for us? So like for example, given like the graph, we can tokenize it, and with text, we have the LLM predict like something about the graph. Or like given like a graph neural network encoding or something, we have the LLM predict something about the graph. So kind of like the general approach for this paper was that given like this kind of like this organization of graph, we just kind of talk about what the graph looks like. It's an undirected graph. The nodes are numbered 0 to 4. This node is connected to that node. And then it just simply asks, let's construct a graph with the nodes and edges first, so that basically the LLM kind of like goes through this and like builds a graph in its own words, and then it finally does a prediction, basically. And another kind of like more, honestly, a pretty similar way is like you have, apparently there's something called like a graph standard like XML language, and then you kind of like have LLM generate like contexts by talking to itself, and then it finally does the output. So yeah, kind of like the main strategy for this kind of like representing graph as text and then having LLM talk to itself and stuff, it all seems like the main strategy seems like inputting the text data for the graph, and then have LLMs understand the graph, and then ask questions, and then finally do the output. But yeah, I think like the main limitation is pretty obvious. it's not scalable to like large graphs. Like you don't want to like talk about like a 1000 node graph with GPT-4 because that'll be like extremely expensive. Yeah. So to combat this, kind of like a bit more interesting approach is having the large language models align with the graph neural networks. And honestly, this paper might be kind of like should exist in this previous section, but the basic idea is like we first have the graph neural network process the graph, and then we have these kind of like graph positional encodings in the exact same way I mentioned before, in like the shortest distance way. And then we just add them to the LLM. So these are like graph tokens of like every single node with the positional encodings and stuff. And we add it to the LLM, and then it can kind of like work with graphs with like graph nodes and stuff. So this only needs like all the new tokens needed. It's just like the graph tokens, the number of graph nodes and stuff. And yeah, so I think this should exist in the previous section, but I think it's very interesting. But another method that I wanted to highlight was basically inspired by BRIP2. And actually, let me see if I have questions. Will the LLM use something like tool or JSON? So in this case, only JSON, only schema. I didn't see like much mention of using tools and stuff. Yeah. But yeah, basically kind of like if you have been around Hugging Face like CB community stuff, you might have like seen like I think Joko present about BRIP2. But basically the idea is you have the input text. So there's a text transformer and an image transformer. And both of these are like, usually for clip you train with like a batch size of 1 million, and like both of these you have to train from scratch. But we have like a frozen image encoder and like a text encoder. And the basic idea is like we plug in the input image into the cross attention, not the learned credits, in the cross attention. And then we have like the learned credits kind of like try to encode these image information into these learned credits so that it can do like stuff like contrastive learning with image text, which is basically like figuring out like an image text like representation where like if you Google cat, it can get cat images. Or like maybe a more like understandable example is like given these images, we can caption this image using text. So basically there is a way to connect pretty cheaply like pre-trained image encoders and pre-trained text encoders. Yeah, at least I think this text encoder isn't pre-trained, but yeah, overall like there's a way to connect like different modalities pretty cheaply like this. So there's this new paper called Gitmo, which is like basically like a graph neural network with like molecules, and the idea was pretty much exactly the same as that, but using graph embeddings. So here we have the graph, we have the graph neural networks like embeddings, and then we add it to the cross attention, and we bottleneck with the learned query so that it can do like graph tasks with LLMs and images and so on. Yeah, so honestly, this is like the favorite paper I found from this survey. Yeah, any questions? Yeah. Yeah, let me know if you all have questions about this, because at least I had a bit of an issue figuring this out before. Yeah, and also, yeah, okay, nobody, yeah. Okay, so the limitation that the paper talks about for this is that basically it suffers from it. It says that its capacity is bottlenecked by graph neural networks, and in that like it if like adjacent nodes are not similar, which is like one of the main assumptions that graph neural networks have. If adjacent nodes lack similarity, then this doesn't perform well. So yeah, it's like a bit bottlenecked by graph neural networks, which is a bit expected, I think. Okay, then I think we went through all the LLM as like predictors, aligners, and like encoders. So next we will talk about knowledge graphs. So for knowledge graphs, it's like a basically it's like a tuple of like three words. So for example, Arnold Schwarzenegger is a governor of California. So not three words. It's like three like sentences in a way. Yeah, or like Schwarzenegger style predator or something like that. And basically, we want to like modify the LLM slightly so that we can kind of like encode these facts into them so that they perform better in a way. So the first paper that I think the paper highlights is this K-BERT one. And basically the idea is you have the sentence, Tim Cook is visiting Beijing right now, Beijing now. And then we have like the knowledge graph tuple, Cook CEO of Apple, and also Beijing capital of China, and Beijing is a city. And what happens next is basically I don't think you need to like worry about this too much, but basically kind of like in the attention matrix or like when the attention is going through stuff, it hides certain tokens for like generation or like when predicting, but it shows it when we are like within the knowledge graph. So for example, for the first like, so for the 0, it doesn't see these tokens and it doesn't see these tokens. But for Tim Cook, these should know the CEO of Apple. So for 1 and 2, it can see CEO Apple and so on. So it's kind of like it's like a clever like prompting strategy kind of with like small modifications to inject knowledge graphs into like the queries in a way. And yeah. Yes. Yeah. Honestly, I like the examples that Wikipedia had, which Arnold Schwarzenegger is a governor of California. Yeah. So knowledge graphs, the main use of knowledge graphs is to encode facts. So like the main idea is like we can use them to like to like avoid fake news in a way, so that everything encoded in a knowledge graph, like for example, it's very used in medical stuff. Exactly, yeah. The ideal goal is that the large language model always generates correct stuff. So knowledge graph is like for that basically. One criticism I have of them is I don't think they are used for like logic and math, but overall like for factual statements in medical stuff or like news and stuff, I think they are very helpful. Yeah. So yeah, so yeah, kind of in this case, it encodes them like this. But a bit more interesting one was a one called Ernie, and there has been like significant like improvement on this. But basically, we have Bob Dylan wrote Bro or something, And then here we have like a separate multi-head attention thing for those end tuples like California or like Predator and Die Hard and stuff. And what happens here is that these tokens that are separately encoded gets concatenated onto these tokens. Like Bob Dylan, for this, the capital Bob Dylan gets encoded. Honestly, I don't think this is a great example because Bob Dylan and capital Bob Dylan is basically the same thing, but you can just think of Tim Cook and Apple or something like that. Basically, first they are concatenated, and then in this information fusion part, using like, so this is like the free connected layer for the original Bob Dylan, and this is like a free connected layer for the new like the end tuple part. So this is like the fact associated with Bob Dylan, and then finally like a bias. But overall, like it encodes both of these information, Bob Dylan and this capital Bob Dylan, into like one like fusion matrix. And then we have these two like free connected layers to get back the original Bob Dylan and like the capital Bob Dylan and like send them out. And what this accomplishes is into the original like words or like tuples or original like tokens, it encodes these facts into them so that it can kind of like it knows the full context behind all these tokens in a way. I actually kind of like, I don't know about Devin, but one thing I would say is like I've seen people use knowledge graphs as like replacements for RAGs, or like try to make like an efficient knowledge graph like query extractor thing to kind of do pretty much like RAG like stuff, but more reliably in a way. So yeah, kind of like I think this approach is pretty cool, but one kind of like limitation of it is like basically for when we want to tune LLMs and stuff, we want to like do it in a very parameter efficient way, like LoRa's and stuff. And this is definitely not like that because we are directly modifying the parameters and we are adding this information fusion stuff. So you can't like with like regular levels of hardware, you won't be able to do this like with like Llama 370B or something. So yeah, Microsoft had another paper called Color, Knowledge Augmented Language Model Adaptation. And the basic idea is basically kind of like when you mention New York, there's like this kind of like database of like embeddings which from the paper description seem to be updated with like a GNN with aggregation and update, where like it gets like the knowledge pairs of like New York City of USA and then calls it into this embedding. And given this embedding, we have like a scale vector and a bias vector, where the scale is initialized to 1 and the bias vector is initialized to 0. So in the beginning, nothing happens, but as it gets tuned, it kind of like modifies the network or like these tokens by like a certain scale and bias so that it can encode these embedding informations in a way, or these knowledge graph information. Yeah, does that make sense? It took me a while to figure this out. But the benefit of a knowledge graph is you do not need the embedding. I don't think I fully get it, but my understanding is the benefit of a knowledge graph is that you can kind of rely on it as facts. Like you can rely that you can for certain say that New York City is a city and it is like it's part of USA, kind of like that. Yeah. Yeah. Exactly what he said. Okay, so now for limitations. So yeah, obviously for all these ones, I think you need to like train the LLM a tiny bit to make it work. So kind of like one thing you might be asking is like, well, how can I just use knowledge graphs with like GPT-4 for like a better like fact-based output without hallucinations? And the answer, well, one idea was from this paper was, why don't we just plug in the knowledge graph? So like, for example, here, given this knowledge graph, it just plugged in all the tuples of the knowledge graph, and then it asked a question, and it apparently with just that it performs well a bit, but I think it's a pretty preliminary approach. Yeah. A bit more interesting approach that I found was by this paper, and basically the idea was let us first like generate an answer from the LLM, and then we extract the claims that the LLM makes, and then we get the entities, and then we do a knowledge graph to check if all the facts are correct, and then verify them, and then update the response until like given all the knowledge graph like fact checks, it says like, oh, these are all correct, you know. So basically, it's like an iterative like querying approach of like progressively getting like better output and stuff. Another like a bit more interesting idea was like given like a prompt, it defines it and stuff, and gets like the knowledge prompt pairs using ChatGPT, and then you just plug it into a GNN. So you just plug it into a GNN, and you get the labels, and then just like, yeah, I think this is a bit similar to the LLM as encoder idea, but yeah, basically you just plug in these knowledge pairs into a GNN to like, I think like classify these texts in a way. So yeah. So I think we are almost finished. The basic idea of these papers was like, since GNNs suffer from like out of distribution samples, and LLM seem to help with it, kind of like maybe LLM plus GNN is the future. Yeah. But yeah, kind of like, also this paper suggested like doing more of the foundational work, like a bit like was mentioned here with like BRIP2 and stuff. So where like you train it a bunch of multimodal data, and it says maybe this is the future in a way. Like if we have like social networks and like stuff, if you have text, image, and graph, and just train across like the entire internet, maybe that's the answer to making graphs perform well. And another thing that it mentioned was, yeah, since it's like, since the computation is O(n) squared, there needs to be like a lot of innovation in like the efficiency department. Yeah, I guess like a bit of stuff added last minute, but for applications, there's stuff like recommendation systems, where like based on like users and films they watch, you can kind of like, given a new user in a new film, you can kind of try to predict how they act. Like that's one application of graphs. And one application that might be interesting for like LLMs too is like, given like an input graph, kind of like have it predict the next actions and like objects to act on, so that it can kind of perform well and stuff. But yeah, kind of like overall, I was a bit surprised that there wasn't much on graph planning for LLMs that I could find in this paper. And also, there wasn't much on like graph generations, like adding nodes to graphs, or like improving math capacity and logic, and also like quantizing graphs, but it might be a future direction. And these are like libraries that like do open source library that does like graph training with LLMs, which honestly I thought might be a future direction stuff. But overall, thanks a bunch for listening to my presentation. Oh, we finished like within 1 hour. Okay. Was correct, but thank you. Thanks a bunch for listening. Yeah. Yes. Sorry for it being like so many papers. I wasn't sure how to present like all those papers because there were like 100 of them, but so there's definitely some papers I'm missing from the paper, the original survey paper, so I recommend checking them out. But yeah. Okay, hope you all enjoyed. Yeah. Any final questions? Okay. So for the next presentation, I'm not sure when it will be, but I'm pretty sure like lunar flu or maybe I will think of something to present. But yeah, overall, thanks a bunch for listening, and I think all that was recorded, so I will upload it on YouTube. But hope you all have a